Okay, we're live.
Good evening, good afternoon, good morning, everyone. We're just going to wait a minute or two for our guests from all over the world to join us. So we'll give a minute to let the audience build here, and then we'll get underway. Welcome, everybody. Okay, we're just under a couple of hundred participants joining us today, so let's get this SETI talk underway. Exoplanets. So the very name conjures up something exotic, something otherworldly, and even a bit mysterious. What is an exoplanet exactly? Well, an exoplanet or extrasolar planet is a planet in some other solar system orbiting a different star than our own sun. Up until the late 20th century, the existence of planets outside our solar system was unknown. The first exoplanet discovery was not even confirmed until 1992. But even then, it was not known whether extrasolar planets were rare or common as a phenomenon. Thanks in large part to NASA's Kepler and K2 missions, from their launch in 2009 to termination in 2018, we now know that planets are ubiquitous, and statistically, they outnumber the stars in the sky in the Milky Way galaxy. We also know that roughly 20% of these planets are rocky, Earth-like worlds orbiting in the so-called habitable zone of their host star, where liquid water can be present in principle, and therefore potentially life could take hold. As such, the number of Earth-like habitable zone planets in our own galaxy alone is estimated to be several tens of billions. So think about that for a minute. Several tens of billions of potentially Earth-like worlds in our own galaxy. Needless to say, if you work at an organization like the SETI Institute, that kind of statistic is clearly good for business. Closer to home, the news of possible signature of life in the atmosphere of our neighbor planet Venus is for the moment dominating the news on planetary science. But our research and understanding of exoplanets outside our solar system has only just begun. While NASA's Transiting Exoplanet Survey Satellite mission, or TESS, is currently mapping the entire sky for nearby planetary systems, 3 new European missions are planned over the next several years to find and characterize new exoplanets with an emphasis on Earth-like and habitable zone worlds. Good evening, ladies and gentlemen. If you're joining us from Europe, good afternoon, good morning from the United States, and welcome to the September edition of our now famously virtual SETI Talks, the monthly lecture series produced by the SETI Institute in Mountain View, California. I'm Bill Diamond, President and CEO of the SETI Institute. We're a nonprofit research and education institution whose mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe. Like people the world over, we're presently carrying out our work from home, but our research and education and outreach programs continue even while the lights are out at headquarters. Our SETI Talks series has been running for more than 10 years, and if you explore the series on our YouTube channel, you'll discover literally hundreds of lectures, debates, and panel discussions featuring many of the world's foremost researchers, educators, and explorers in space science, covering an extraordinary range of topics. Normally delivered to a live audience in the San Francisco Bay Area, the series has been virtual since April, but this is giving us the opportunity to reach a truly global audience and share our stories and our science with people the world over in a live format. So I'd like to welcome all of our registered guests joining us live tonight on our Zoom channel, and also say hello to our friends and followers together with us this evening on Facebook and YouTube. Today marks a very special first for the series, as we've timed the talk for a European audience to accommodate our guest speakers and also honor our friends and colleagues at the European Space Agency. We always love to know where you're joining us from, so if you're on Zoom, use the chat function to let us know. Maybe you have to use the Q&A function. In any case, try one or the other. Let us know where you're joining us from. And if you're joining us on Facebook, for example, you can use the comment section. We have special interest tonight, as you'll see, in guests from Switzerland, Germany, Italy, and the UK, but we delight, of course, in reaching the far corners of our planet. So please tell us where you are. As we do every talk, we like to poll the audience to find out who's joining us for the first time and who's a regular. If you're with us on Zoom, you'll see a pop-up on your screen where you can let us know. Select the answer that best describes experience, and we'll post the response for you in just a few minutes. Tonight, we're traveling beyond our solar system to other star systems and their planets. We're joined by three esteemed scientists, each a principal investigator on one of the three upcoming European exoplanet missions. Introducing our speakers and leading the discussion tonight is Dr. Frank Marchese, senior scientist and astronomer at the SETI Institute, and Frank is a member of the science team that took the very first image of an exoplanet using the Gemini Planetary Imager, or GPI system. We will have time for audience questions after the moderated discussion, but please note that we're not able to answer all your questions. Also, please pay attention to the fact that you won't necessarily see the questions in your own Q&A section, but we do see them all. My colleagues, Rebecca McDonald and Simon Steele, will be fielding your questions on Zoom, posted via the Q&A function you can see at the bottom of your screen. We may not have time for all your questions as noted, but we will do our best to address the most intriguing ones, so be clever. And now it's time to buckle up and get ready for a journey to interstellar space, to new worlds as yet undiscovered. And with that, I'll turn the proceedings over to our expedition leader, Dr. Frank Marchese. Frank, please take it away.
Hi, thank you, Bill. Thank you, everybody, for being here. So I'm going to be short. I'm not going to give a very long introduction because we have a lot to talk about today. So this could have started like a typical joke, right? We have a Swiss, an Italian, a German that meet in a bar, and what they do, they talk with the French bartender about what? Exoplanets, because that's the most fascinating topic of conversation at the moment, I think, in astronomy. But more seriously, let me just introduce you the three speakers we have today. So first of all, we have Willy Benz. Hi, Willy, how are you?
Hi, hello, I'm fine.
Willy is a professor of physics at the Physics Institute of the University of Bern. He's a director of the Swiss National Center Planets, dedicated to the study and formation, evolution, and characterization of planets. He's also the principal investigator of CHEOPS. He chairs as well the European Space Agency Space Science Advisory Committee, and is the elected president of the ESO Council. Then we have Heike Rauer. Hi, Heike, how are you?
Hello.
So Heike is the director of the Institute of Planetary Research at the German Aerospace Center, the DLR. She's a professor for planetary science at the Free University of Berlin. She's also the PI of the PLATO mission we are going to talk about today, which will study the planets in the Milky Way. She's also a co-PI of the Next Generation Transit Survey, which is part of the European Southern Observatory. And then the first speaker is Giovanna Tinetti. Hello, Giovanna.
Hello, good evening. Great to be here.
She's the head of the astrophysics group at UCL Department of Physics and Astronomy, and the director of the UCL Center for Space Exochemistry. We're going to talk about that as well. She's a principal investigator of ARIEL, an ESA mission, principal investigator as well of the European Research Council funding programs called ExoLight. So as usual, we ask our speaker to give us a brief introduction about their research related to the topic of the conversation, which is the European mission and the search and characterization of exoplanets. So let's start with you, Willy. You can share your screen.
Hello, yes, I will try to do this. Here we go. Should be fine. Now I need to be able to start this. Here we go. Okay, good evening, everyone. I would like to talk to you about the CHEOPS satellite, which stands for Characterizing Exoplanet Satellite. And this satellite was launched on December 18th last year. And what the proof that it's been launched is you can see the trail in the sky. It is up there and is even transiting a very bright star here. So you can see that we're there. It's the first ESA small mission. And as such, it comes with a number of constraints that I don't want to elaborate, but I'm happy to answer any questions. You see on the right side here some images of how the satellite looks like. It's basically a 290 kilogram satellite, which is about 1.5 meter in size on all sides. It's sort of a cube, 1.5 meter, and it carries a single payload, which is a space telescope with a primary mirror of 32 centimeter, which has been optimized against stray light. So what we want to do with this satellite is to make ultra high precision photometric measurements of bright stars already known to host planets. And you see here an example of one of these light curves that we're trying to measure. It's a measurement we did during the commissioning of the satellite. So when the satellite was fresh into space, we opened the cover, which was quite some tense moment, but then we could measure this light curve. And we realized that we got very, very nice result with a 15.5 ppm noise level. The satellite orbits at 700 kilometer altitude. It has a polar orbit so that it flies always about the day-night terminator and always observes the planets or the stars above the night side of the Earth. So we, again, minimize stray light that comes into the telescope. And the nominal lifetime is 3.5 years, but we cross our fingers that it lasts a little bit longer. Finally, the satellite is a result of 11 European countries and ESA working together. And the cost to ESA is 50 million euro, while the total cost is about 100 million, including launch and operation. So it is really a small satellite, also budget-wise. Now, again, we want to characterize planets and not discovering. And I think this is the key message about CHEOPS. CHEOPS is not about discovering new planet, it's about better characterizing the most interesting ones we already know. And we want to do this by means of these ultra high precision photometric measurements. And the way it works is as follows. It's called the transit method. You have a star orbit, a planet orbiting a star. And if the inclination of the orbit is just right, the star passes in front, the planet passes in front of the star and goes behind the star at times. And during its orbit, you see different phases of the planet. And if you then look at what light you receive from the system, you don't see the planet, you don't see the star, you receive the light from the whole system. And you monitor how this light looks like as a function of time. If we start in the back there where the planet is hidden behind the star, what we measure is a light that varies about like this. It is, you see the star alone in the back, and in the front, when the planet passes in front of the star, you hide a bit of the star and you receive the shadow, and therefore your light dips. And the depth of this decrease in light gives a measure of the relative size of the planet to the star. And if we look at what it looks in reality, if Jupiter passes in front of the sun and some distant aliens look at it, they see a decrease in light of about 1%. If the Earth passes in front of the sun, it results in a dip of 0.01%. And this is really small. And as an illustration, you can see here what happens when Venus passes in front of the sun, and you see how much of a surface it hides. So this means really you need extreme precision. And for CHEOPS, we want to reach 0.002% or 20 ppm, in other words, precision to be able to measure the light of the star during the transit. Now, what do we want to do with this precision? Well, the CHEOPS science is divided in two parts. There is a guaranteed time observations, which is 80% of the observing time, which is defined by the CHEOPS science team. And then we have a guest observers program, 20%, which is attributed on a competitive basis, an announcement of opportunity issued by ESA, who sorts then out the proposal. The topics are several and very diverse, from accurate sizing of the planet, in order to look at the mass-radius relation, atmospheric phase curves when we follow this light and measure a little bit the light reflected by the planet in different phases around the star. We want possibly detect exomoons, rings, or any kinds of feature. We might even discover additional planets, because when we look at the system, you might see an additional one passing by that you didn't expect to be there. And then we have this, what we call CHESS, which is a joint collaboration with the TESS mission. So CHEOPS and TESS made CHESS. So that is a joint venture we have with the TESS satellite. And also all these targets, because they will be very well characterized, will be golden targets for actual future facilities such as JWST, the ELT, or ARIEL, which you will hear more about in a minute. And then there's all the science covered by the guest observer program run by ESA, and that we haven't had any results from that for the moment, so I cannot tell you too much about what the guest observers are proposing, because the two programs are quite strictly separated. And this closes a little bit about what I wanted to say about, as an introduction, about CHEOPS. Thank you.
Thank you. Thank you, Willy. So Heike, you are going to talk about PLATO. So we're ready. Willy, can you stop sharing your screen?
Yeah.
You are mute, Heike.
Sorry for that. I did not want to disturb Willy talking. So welcome, welcome everybody. It's a great pleasure for me to be able to introduce the PLATO mission. So PLATO will follow CHEOPS, and let me follow Willy by starting with the science that we want to do with PLATO. So with PLATO, we want to detect planets, so new extrasolar planets around other stars, and in particular, planets which are small, that means in particular Earth-sized planets in the habitable zone or of solar-like stars. And I will explain in the next slide what this habitable zone means. We want to determine their precise planetary radii and masses and mean densities. Why? Because mean densities are very important to distinguish the types of planets, at least as a gross indicator. For example, the Earth, a planet like the Earth has a mean density of 5 grams per cubic centimeter, and Jupiter, it's about 1. What does that mean? Well, it's the difference in density between a rock and an ice cube, so, to have a comparison. So the mean density is, for geophysicists, the first idea what kind of planets we are looking at. The second indication then would be the atmosphere, but that will be discussed by Giovanna. In addition, we want to study the age and determine the age of planetary systems. And of course, like with CHEOPS, our mission will provide targets for atmospheric studies, for example, James Webb or ARIEL or ground-based telescopes. So which are the methods we are using? Willy already explained the transit method, so I don't have to go into detail with this one. And PLATO will apply this method from its photometric light curves. And in addition, it will use the photometric light curves to perform astroseismology. So what is astroseismology? You have heard about seismology for the Earth, so earthquakes, which allow you to detect waves going through the interior of the Earth and get an idea about its interior. Well, stars don't have earthquakes, but a star is like a big gas bowl, and it has some. It's moving. Yeah, it's expanding and shrinking, like shown here. Of course, grossly exaggerated, but this little movie shows the principle. And this is you can see in variations of the light curves and get some knowledge about the stellar interior, its radius, its mass, and in particular its age. So these two methods, which work with light curves that come from the satellite, we are combining with a ground-based follow-up program. A ground-based follow-up program which is looking at the planets that we detected by transits to get their masses. This works, this is applying another technique to detect extrasolar planet, the so-called radial velocity technique. And this technique observes the wobble of the star as the planet is moving around the star, as shown here. So if we have these, we have the planet mass, we have the planet radius by combining these two measurements, and we have the age of the system. So when we have this, we get the mean density of the planets and their age. And why do we want to do that? Well, I've illustrated this a little bit in the slide here. Planets are not static, they evolve with time. If you take the Earth, for example, it started like a hot magma ocean, and this ocean was outgassing an atmosphere, a water atmosphere, and then a carbon dioxide atmosphere. And then life came and changed again the composition of our atmosphere. So if we are able to get a very good timestamp on the planetary systems, we know how old they are, with measurements like PLATO, together with ARIEL, together with future missions, we will be able to compare planetary systems and in different evolutions, at different evolutionary stages, because we see the planets of different ages on the sky. So why do we have PLATO after CHEOPS and TESS? This is a question I get very often, so I have a slide for that. And this slide to the left is showing it in a diagram that shows the stellar mass here. Here's one, this is one solar mass, so our sun is here. And I've shown the planets with the distance to the sun. This is Mercury, this is Venus, and this is Earth. And then you see this green band here. This green band is what we call the habitable zone. And maybe it's explained a little bit better in this diagram over to the right. You have the sun in the middle, the planetary system. You see again this green belt. And this green belt means a planet like an Earth can have liquid water on the surface. So you see here Venus also in the green belt. Why? Well, because we choose it optimistically and we speculate maybe Venus also had water at its beginning, but certainly Mercury was too hot, always too hot. So if we go to stars that are smaller than the sun, they emit also less energy. And that means you can move closer to the star and still be in the habitable zone. The habitable zone shrinks and is closer to the star for these cool M-dwarf stars, as we call them. So this is why this band moves to the left here in this diagram. Here are the short orbital period planets, and the orange distance shows you the detection range of ground-based surveys, CHEOPS, TESS, also most of the Kepler targets are here for the planets for which we have a measured radius and mass, because this is what we are after. So you see already some dots here in the habitable zone, and we will get many, many more from TESS. But these detected and characterized extrasolar planets, they all orbit this low mass cool stars. So they are very interesting on their own, but they are not similar to our solar system. And this is why we argued successfully that we need another mission to follow this, the mission PLATO, which will cover the full distance range and in particular detect planetary systems and characterize them for their mean density and age around solar-like stars. In addition, as you will see, we will also expand the distance range for the cool stars, so we might be able to find outer planets in these kind of planetary systems. So a last slide, well, how does the mission look like? PLATO is ESA's third medium-class mission. The payload is developed by it's a joint development of ESA with an international mission consortium of 25 countries. And the launch of the mission is planned for the end of 2026. The design of PLATO is a bit unique for a space telescope. You see it here. Well, we'll come back in a few minutes. It's not one big dish. Maybe it's something that you're more used to for telescopes. The optical sensitivity area is divided into 26 cameras, small cameras with an aperture of 12 centimeters, refractive cameras. You see here in the bottom, you see these, the camera, as an example, one of these 26 cameras. So 24 cameras are used for photometry to get light curves of our stars, and 2 cameras are used for the fine guidance to keep the position of the satellite very, very stable, which is important to get the good photometry. Our baseline operation is for 4 years, but we will have consumables on board for 8 years. So we are looking forward, and I'm sure we can convince ESA, if we are doing good science and we get the great results we hope for in the first 4 years, that we can extend the mission to look for really long period planets. And with this, I hope I gave you a first overview of PLATO, and I'm looking forward to your questions.
Thank you, Heike. So let's stop sharing, and Giovanna, you turn to describe ARIEL.
So good evening to everybody, or good morning. It's a great pleasure to be here, and thanks so much for the invitation. So before I say a couple of words about ARIEL, I just want to say that in the past years, as my colleagues have pointed out, we have discovered all these great planets, more than 4,000 now in the galaxy. And all these planets seem to suggest that there is a huge diversity out there compared to the planets in our own solar system. We're seeing planets that complete one orbit in less than 1 day, or extremely hot, planets that are very cold. So really, really huge diversity. And so we have all this question that we want to start answering as scientists, but also as human beings in the next decade. And among this question, we have what's our exoplanet really made of? What's the weather like there? Perhaps it's a bit of a British question. Why these planets are so diverse, why the solar system perhaps is not the paradigm, the key example of planetary system in our galaxy. And more in general, we want to try to understand how planets are forming and evolving our galaxy. And today we have a way to start answering all these questions, and a way to start giving some answer is to observe the atmosphere of these planets. The atmosphere is the gaseous envelope around the planet, and we have now a number of techniques that can be used from space on the ground to find out what is the chemical composition of this atmosphere. So what are the molecule present, water vapor or methane or carbon dioxide, and so on and so forth. But also we can understand where there are some clouds, what is the temperature structure of those atmospheres. And even today we have telescopes that can deliver this kind of information. In particular, Hubble and Spitzer have delivered pioneering observations about the exoplanets, about the atmosphere of a number of exoplanets. And JWST and our facilities from the ground clearly will follow this work. But the problem is that if you want to study not just a few tens of planets, but really a large number of atmospheres, then you really need to have a dedicated mission from space, because it really takes some time to look at all these planets. And this is why we have proposed the ARIEL space mission to the European Space Agency back in 2015, and ARIEL was selected to be the M4 space mission for ESA to be launched in 2029. So the key selling point of ARIEL is the ability to look at the atmosphere of about 1,000 extrasolar planets. And the idea is that we want to collect the light of all these planets, but not just collect all the light together. We want to, well, we will use like a prism that will split this light coming from the atmosphere of this planet into multiple wavelengths or colors. And through that information, we can work out what are the molecules that are absorbing in those atmospheres, what's going on there, what is the temperature, and other questions. And we want to repeat that for a large number of planets, small rocky planets or bigger one. We will focus mainly on warm and hot atmospheres, because these are the ones that are easier to observe. But hopefully we can also look at a few more temperate planets. ARIEL will be built, well, of course, ESA is in charge of delivering the spacecraft, but the payload will be delivered by a consortium that is including a contribution of 17 ESA countries. And there is also NASA contribution that has been approved earlier this year. So we are very happy to have the American team joining us. And as a last slide, if you're asking yourself how you can contribute to ARIEL, well, I have some ideas for you. We have a number of citizen science programs connected to ARIEL, and in particular, the ExoClock program is being very successful. Basically, we are receiving the help of many amateur and professional astronomers all around the world. And if you go to the exoclock.space website, basically we update regularly what are the planets that you could help us following up with your telescope from the ground to make sure that when ARIEL is launched in about 10 years' time, we will know exactly when the planet is transiting, and so we'll have a much more detailed information about the orbits when the transit is happening, but also the stellar characteristics. So if you want to help us in making sure that our list of planets is the best one, then ExoClock is a possibility. Thank you for your attention, and I'm more than happy to respond to your question if you have any.
Thank you to Giovanna, and thank you to all of you. So the next step, we're gonna have a simple conversation. I have gazillions of questions, of course, because it's very rare we have the three of you together like this. And of course, there is some scientific questions and not scientific questions. I'm gonna start by the non-scientific question here. Could you, one of you, explain to us why the sudden interest from ESA for exoplanets, and why ESA has selected 3 missions basically for the next 20 years for the study of exoplanets? Maybe Willy can start talking about the selection process for CHEOPS, and each of you later for PLATO and ARIEL as well.
Maybe I can take the part of the question that is addressing the sudden interest of ESA, because the interest is not so sudden. The first space mission that was designed to search extrasolar planet was the Corot mission. It was a French mission led by the French agency CNES with European participation, so on a bilateral basis. So Germany was part of it, for example, and Switzerland, and ESA was part of this. So ESA was already involved in the first mission that was going for extrasolar planets, and the first mission that detected a rocky planet, cohort 7b. You know, these detections are numbered. And 7b, followed later by Kepler 10b, were the first planets where we had a radius and a mass, and we knew they were really rocky. Of course, the orbital period was very surprising. I couldn't believe it when Corot 7b was detected. My first feeling was it can't be true. You can't have a planet with 20-hour orbital period around a star like the sun. But it was confirmed, it's true, it was real. And like Giovanna said, it was also a start of a learning process about the huge diversity that planets have, which is very exciting, but also raises many, many new questions. And that then stimulated these future missions that followed Corot to address all the questions that were coming with these exciting detections that we have. So that is the very beginning in this.
So it's basically Corot has been basically the first mission, and then you built a community of exoplanetary scientists, and now there is a significant one in Europe as big as there is one in the US and elsewhere in the world. Exactly. So Willy, maybe could you tell us a bit why ESA selected CHEOPS, for instance, and what was the process of selection and the main reason this mission was selected?
Yeah, ESA wanted to start a new line of mission. ESA's portfolio is, so to speak, composed of 2 types of mission: the M mission, medium missions, and the large mission, the L ones. And ESA in 2011, 2012 decided to add a new line of mission, a small mission, that should have a very fast turnaround, be relatively cheap, and allow also medium to smaller countries like Switzerland to play a role in the developing and leading missions. And so this was the idea, and it wasn't clear if it would be successful, if there would be enough proposal, enough good science you can make with a small mission. So ESA issued a call for ideas in 2012, and there were 26 proposals handed in response to that call. And there was an advisory panel that decided, they made the selection, and out of these 26, CHEOPS was selected. So we were lucky to be the first small mission ever selected by ESA. We sort of the pathfinder of the whole thing. It was we were clearly told that we were a test balloon. We better be successful because otherwise we stop small missions at ESA. So we'll see how it works out, but that's, so to speak, the story. And so it means also that everything had to be invented, because ESA's missions are medium or large, not small. ESA's mission takes some time because there are a lot of countries that have to agree on something, and consortiums are huge. It takes time, but then it works. And so a lot of things had to be invented for a small mission to go fast and remain relatively cheap.
Okay, so, and all of you in your conversation mentioned kind of synergy activities with other missions or ground-based telescopes. So I know it's a very common question that you're getting. Why do we need to go to space for those missions? You have different reasons, so maybe each of you could answer to these questions, hopefully. Can start with Giovanna, maybe. Why do we need to go to space to understand the composition of the atmosphere of a planet?
Well, probably in my case, because you want to look at molecule preferably in the infrared light, key molecules that we are looking for in those atmospheres, which include water vapor or ammonia, or carbon dioxide, a long list, they all have a very distinctive signature in the infrared light. And our own atmosphere is actually quite opaque in the infrared. And so you really have the problem of the Earth atmosphere if you're trying to do that work from Earth. It's not impossible in certain bands, but clearly always quite limited. And if you don't have that limitation and you are in space, then you can be very efficient and you can really look from one planet to the other very efficiently. And certainly for ARIEL, this efficiency is also very important if you want to keep up not just the quality of the observations, but also the number.
What about you, Heike?
Yeah, for photometry in white light, we are doing it from the ground as well. For example, the NGTS project is doing it, and there are several others doing this. But the atmosphere is posing a limitation for the small planets. Because when you look in the sky tonight, you will see the stars, hopefully, if it are not clouded out. But if you see the stars, you see they are twinkling. And this twinkling is not the star, it's the atmosphere that causes refraction and variation in the light intensity. And this is a limitation for the transit method from the ground. So we can detect down to about Neptune-sized planets with transits from the ground. That has been done. But what we are after is an Earth around the sun, and we want to observe many stars at the same time, and with very high precision. And for this, we have to go to space. This cannot be achieved from the ground.
And you, Willy, why do we need a CHEOPS in space to do this?
Well, it's for the same reason as Heike, because we use the same technique to measure the same quantities. So it's basically a question of precision and getting, for the small objects, you just need to go above the atmosphere. The precision you need to measure the light, the dipping, the small change in light when the planet passes in front of the sun is so minute, it's so minuscule, right? It's 20 parts over a million. That you want sort of a precision to say something meaningful about the planet, and that you just can't do from the ground.
So you cannot detect an Earth-like exoplanet around a G-type star from the ground by transit, or that's possible?
If you would use a very big telescope and observe, maybe, but the point is if you're searching, like PLATO, we are looking in our core sample, we will look altogether at 15,000 stars in two fields. So we have two long stairs in the baseline program of 2 years each. We know it's too short, we want to observe longer, so we hope for the extension and observe longer, but let's say two fields, 15,000 stars. And you need a wide field telescope to do that. And from the ground, that is simply not possible and completely impractical. It won't work. So we need to go to space and do the job from there. But there we can do our 15,000 core sample and get another 250,000 on top of that, where we will not detect on some of them we will still detect on Earth, but we will have difficulties to do the astroseismology in the host stars because they will orbit fainter stars. But we can get a large statistics like Kepler and TESS. The difference to Kepler and TESS is not only that we stare longer than TESS, this Kepler has done as well, but we are looking at the brighter stars. And the brighter stars allow the astroseismology and they allow the follow-up with radial velocity from the ground, because that was so unfortunate with Kepler. With Kepler, we had so many small radii detections, but for most of them, we could not get the masses from the ground because the stars are too faint. So, so PLATO is filling that gap by doing this job for brighter stars.
That's a
this
perfect.
Is actually something we learned on the way. You know, it is not it's not a fault of Kepler that it observed fainter stars. We really thought, everybody thought, also in Europe, that this was the thing to do at the time. But then we learned, no, just the radius is not enough. We have to get the mean densities because planets are so diverse.
Yeah, that's the transition, basically. That was my next question. So those missions are great because they are going, for you, PLATO in particular, and CHEOPS as well, will be looking at some bright targets, confirm and measure first transit and secondary transit and also phase functions. So you get more information on the planet itself, and then you can use this information to get follow-up on ground base or on maybe space telescopes, others like JWST. I'm assuming you have been thinking about Hubble Space Telescopes as well. So what kind of information you expect to get by adding those additional space telescopes that will come in the future, and also the extremely large telescopes?
So maybe I can set from the transit method has two advantages. It's first, the transit method allows for the gaseous planets to get the atmosphere. This Giovanna will talk about, but it's also the only method that gives you a direct measurement of the radius without applying modeling. So for transiting planets, we'll have the radius and the mass and the mean density with high precision, and that gives again input models to input parameters to atmospheric models and constraints to interpret the atmospheric parameters. And also it helps to select the good targets for atmospheric missions, because even with a space mission like ARIEL can do many planets, thousands of planets, but if you think about the small ones, you will need a lot of observing time, and you will need to know your targets beforehand, also for the transit method and transit spectroscopy method.
Okay, so before we go to the next question, I remind our viewers that we're gonna soon take their questions so they can start posting them on the Q&A. I saw there is already a lot of them, in fact, way more than we will be able to answer. Something that someone mentioned to me, all your missions are great, there will be a ton of data. How are you gonna be dealing with that much frames? How are you gonna bring them back on Earth, first of all? How are you gonna analyze them quickly? How are you gonna select the ones which are interesting? Publish all those papers? Do you have a strategy? Do you have, how do you organize a team to do that efficiently, for example? Maybe Willy, you can start answering since you have a mission already flying. So maybe you can tell us what the mess you are into at the moment.
No, CHEOPS has an advantage. We're looking at one star at a time. We're looking at stars that are already known to host planets. So we are not confronted with data deluge as the other mission. So in that sense, we are safe from these kinds of problems. We don't have any false positives. We don't have any problems that usually the people running a search for exoplanets have. We are just characterizing. So we fight for precision. So our game is to target the most interesting targets that we can find, the sort of Rosetta Stones of planetary systems, and try to measure them to the utmost precision. And that should help us to get better constraints on our understanding of the formation and evolution of these systems. So we don't really have a data problem. We don't get huge amounts of data, actually, not at all. But we still had a large science team that spent the last 4 years in finding or in agreeing what the 300 or 400 most interesting objects up there are. And so this led to many discussions, and the list is changing and evolving with time. As you know, with every new test discovery, we're asking ourselves, well, is this now the new best target, or should we change something, and so on. So it's a very dynamical thing. We beam up our observing list every week. We send the list for the next 2 weeks. And so we have some reaction time, so we can really choose. CHEOPS can see a large fraction of the sky, not completely the whole sky, but a large fraction. So we really have a large amount of targets. And we can measure anything that's known. We don't need to measure planets that are close by to the star. We can measure anything as long as we know which star to look at and when the transit occurs. Then we can measure it. It doesn't really matter if it's far or close. We just need to know where and when to look, and then we can get it. So we don't have these problems. I'm glad about that.
So let's see how the other are dealing with the problem.
Okay, so we do have that problem, but it's not really a problem. Why do we have the problem? Well, we have 26 cameras. Each camera has 4 CCDs with 4,000 by 4,000 pixels, 18 microns square. This makes the largest photon-sensitive area that has ever been flown in a scientific mission when PLATO will launch. And it's simply too much to transfer the whole images down all the time. The cameras, the normal cameras for the normal photometry, they are read out every 25 seconds. The fast cameras 2.5 seconds, but the big data volume, of course, comes from the 24. So every 25 seconds, and that's too much to transfer down. So what are we doing? So we use a technique that was already used with Corot and also used with Kepler. We are making cutouts around the star. In Corot, they were called imagettes in the French language, of course. And since we are in Europe and astronomers are very traditional, once astronomers give a name to something, you know, it sticks forever. So we call them imagettes, and they were called postage stamps in the Kepler world. So for those of you who know Kepler, it's the same thing. So you have the star, and you just cut out the part of the frame around this and transfer this to the ground. This has the advantage that you can process the images on the ground. You have all the pixels on the ground. And if you discover that your algorithm can be improved and you can do better, you can reprocess the data on the ground. That's nice. So we will do that for all the stars that are brighter than 11th magnitude for the astronomers in the audience, so for the brighter ones. And for the others, we will do the processing on board. That means we will add up, stack the light curves, the intensity points, and then transfer a data point down corresponding to every 10 minutes of observation. And with this, we get more than 200,000 stars down altogether over the course of the mission. So yes, we have that problem, but there was a solution already, a pathway found from Corot and then Kepler, and we follow that proven methods.
And Giovanna, since you have spectroscopy, you may have another problem.
Well, actually, in terms of data rate, we're a little bit like CHEOPS. We're focusing one star at a time. And so we won't have a problem of having too much data, too many data we to look at, like you could have with SKA or other facilities. But of course, there is an issue of efficiency. We want to be able to look at as many planets as we can, but also do a very thorough analysis. And given that for many of these planets, we will not know anything before ARIEL is flying in terms of atmospheres. The strategy that we are planning is to go first for a sort of survey of the 1,000 atmosphere, not really going too deep, so not a full resolution. And all this data, we call them tier 1, will be immediately released to the public. So basically, we will have no proprietary period on this data, because we really want to have the help of all the scientists around the world to be able then to select the very best out of those 1,000. We want to select half of them and really go into full resolution mode and really look at the characterization of those atmosphere much more in depth. And also that the data policy will be relatively open, because this data will be available after 6 months of proprietary period. So the ARIEL team really wants to see the data being looked at by as many scientists as possible around the world. And really, we want to have the collaboration of all the scientists around the world in order to make sure that we look at the very best possible targets.
Thank you, Giovanna. You just basically answered to my questions related to this. So when this data will be released, will be available to the people? You mentioned for ARIEL, but what about CHEOPS and PLATO? Are you going to release them to the public, to do their own analysis, to scientists? What's going to be the mechanism for that?
Willy first, or shall I first?
Trevor, go ahead.
Okay, we also will finally release all the data to the public, and we'll do that a little bit staggered, because what we said with PLATO, what we want to provide to the community with PLATO is a PLATO catalog. So that means we want to give them the detected planets, the radii, the masses, and the ages. So, so what we'll get from the satellite are and the processing on the ground will be the light curves. The light curves, that is the intensity with a timestamp. This is our kind of raw data, or calibrated data then. And from these we derive the parameters. So we have to find the transits. We have to identify those transits which are false alarms, and those in particular that are good transits for Earth-like planets. And this will go into a kind of filtering process. That means there's photometric filtering with telescopes from the ground, so medium-sized, smaller telescopes. The ones that pass this test finally will go to spectroscopy to determine the planetary masses. And here we will need the really big telescopes that are the biggest ones that are available on the ground, and the best instruments to do that. And you understand this is very, very costly. So we cannot send thousands of candidates to these big telescopes. We have to have a filtering process beforehand that will take some time. So depending on what we are looking at, we will release very quickly. Like we have these 200,000 spectral targets. They will be like the Kepler data set, more or less. Yeah, they will be released very quickly. And then we will have the ones where we need time to do the follow-up. But the community can participate into this follow-up. It's very open. There will be a call for a consortium to form, because we will need all the telescopes around the world, so to say, to do this huge work. And it's not us. So when I say we, I mean the community, the scientists. So we will need to form another consortium to do this ground-based follow-up. And I'm sure I know there are many scientists interested in doing that and participating to this. There will be a call about 2 years before the launch, and I expect that we have to get organized much earlier to get this done. So the data will become public. All data will become public, the raw data, and up to the final products, and we will release them in stacks. in stacks every 3 months. So the satellite looks into a particular field of the sky, and then like Kepler, it has to rotate every 3 months to have the sun in the back, not have the telescope look into the sun. So this defines a natural sequence for the mission. So the data come down, they will be calibrated. There will be a period of maximum 3 months for the core target to produce the science results, the radius, the stellar masses, the ages, and then they will be released. And for the most difficult ones, we will need a little bit longer time for the ground-based follow-up.
Yeah.
Just given by nature, because an Earth around the sun has a long period.
Okay.
You want to add something, Willie?
In our case, it is a 1 year proprietary time for both GTO, so the consortium observation, as well as the guest observers. They have a 1 year time, and then everything becomes public.
All right.
So everything will become public within a year, but it will go much faster than that, because our reward for us scientists, right, is to show others what we've done. So we will be publishing as fast as we can to convince people how well we've been doing and what these new results are interesting. So we're not going to sit on the data for one year. So the data will come out much faster than that.
So when shall we expect the first publication with CHEOPS?
If everything goes well, next week, probably.
Oh, okay.
So it's imminent. It is imminent.
All right, good to know. So we're going to take some questions. Go ahead, sorry.
Sorry, maybe I forgot to add that if the scientists want to participate to PLATO, there's the open program as well. So we have 8% of our data rate where people can apply for any kind of science case that is possible with the satellite. And I'm really looking forward to see many of these proposals, because they will be in a different field. There will be great science. And I can tell you for Kourou, the additional programs and the stellar science produced many more papers. And it's nice to see that we proposed these missions for a particular science case that made it win the mission, but there's so much more, so much legacy to come from these. We should not forget about this. There's an even bigger community out there that's waiting for the data, and we'll give it to them.
All right, thank you. So we have, I think, more than 400 viewers right now. So, and a lot of questions. And Rebecca and Simon's gonna pop up on the screen and tell us a few of the selected questions. Then we are ready, Rebecca and Simon.
Okay, thank you very much, Frank. And yes, we have a very large number of questions, so we'll try and get through as many as we can. We'll start off with just a slightly more general one. These are from Amelia and Helena. Maybe to aim first of all at Willie. What's the closest planet that CHEOPS has studied or will study? And maybe for everybody, for your particular telescope, typically how far away are these planets that you're going to be looking at, the closest and the furthest, roughly?
Okay, CHEOPS looking at bright stars. We are looking by definition at planets that are as close as possible to the sun. The closest one is 4.5 light years away. So we are looking at planets within tens of light years away from the sun.
So for PLATO, these are also our prime targets, and then we will go, because we are searching, so we have to have a larger sample than CHEOPS. We will go to tens and hundreds light years. But the bright sample with the closest one is where we will find the Earth's around solar-like stars. So it's similar to what Billy says. And
also for ARIEL, the closer the better, the brighter the better. So in particular for super Earth, which are the most numerous, we will try to get the one that are around the very brightest stars. For the giant planets that typically are more rare, then we can push and go for 100 light years away. But clearly we want to stay relatively close in the solar neighborhood when it comes to small planets.
And maybe we can add that there is enough of them close by to get us busy for a while.
Excellent. I think it's a two-part question. The first part is from Emma, which is Earth is the only planet we currently know that has life on it. So when you're searching for biosignatures, how do you determine what constitutes a biosignature? And then the follow-up question comes from James, and it's if ARIEL detects a biosignature in the atmosphere of a planet, what will be the protocol for making an announcement?
Well, these are excellent questions. ARIEL will not necessarily focus on habitable planets. I mean, the main focus of the mission, in a certain sense, will be on planets that are relatively warm and hot. So almost by definition, not necessarily habitable. But that I think is even more necessary if you want to understand habitability, because as you're quite correctly saying, the Earth is the only example that we have so far of a habitable planet, or maybe Venus, let's see. So I think you want to understand perhaps first what a non-habitable planet looks like. And at the moment, we really don't know. We don't have a statistics of planets in the galaxy, even the hot one, not habitable one. We don't really know them. We don't know the intricacies of the chemistry in those planets. The little we know so far seems to suggest that they're actually quite complex objects. And so perhaps our current definition of biosignature, which is based on looking for chemical disequilibria, maybe when you start to have so many planets that they all show chemical disequilibria for other reason than life, I think it's really important to know that, to put the question into perspective. So my hope is that we will look at many planets that are not habitable. We understand what disequilibrium chemistry really means by looking at all those examples. But then at a certain point, perhaps it's not through ARIEL, maybe through JWST or from the ground, we will look at a planet and something strange will stand out, and compared to all the other examples that are not habitable, will sort of indicate that this is a special object, and so really deserve our attention. So that would be my plan.
Okay, thank you. We have well, going to modify slightly a question from Kyla, who is asking, how do we know how old the Earth is? But let's turn this around and imagine the Earth is an exoplanet that you are studying from 4 light years away, 10 light years away. What could you tell about the Sun and the Earth? How would you work out the age of a star? How would you work out the age of a planet and the characteristics? What things could you tell about the Earth without actually knowing anything about the Earth?
Shall I start with the big, and then you can follow, Giovanna? So the age of the system, we can't determine the age of the planet. That's very, very difficult. But what we see is the star, and with the astroseismology technique, we can see the movement, the frequencies of the stars, and this depends on its interior and its density distribution. And from this, we can determine the ages. I don't know how technical I should get, but a star emits energy. It's defining the star. It's burning hydrogen to helium, and it's producing heavy elements in its interior, and therefore its density and density distribution changes with time. And this is what we can determine via this astroseismology technique, to say it in simple words. And fortunately, the planet formation then, and Willy is more the expert on this one, the planet formation then is fast. So a planet can form in a few millions of years, or thousands of years. But when the star is formed, the planet forms quickly. So once we know the age of the star, we know the age of the system. And then I leave for Giovanna to answer what we can learn from the atmospheres. Do you want to do that?
Well, I think you pointed out the important answer to this question, which is actually the star that might tell us something about the age of the system. And clearly age is one of the important parameters, other parameters that clearly we want to explore, because we want to connect those parameters with the chemistry of the atmosphere. Can be the metallicity of the star, so what type of star as well we're looking at. And so, but also the distance between the planet and the star, the mass of the planet. So the idea is that we hope to see in this big parameter space for the star and the planet on the orbits, to be able to link the chemistry of the planet to all these parameters, and through this link really understand what's going on. So in a certain sense, use the chemistry as a tracer of the history and evolution of the planet.
Okay, next question. The next question comes from Aaron, who asks, do you have any advice for young scientists, and in particular for young women scientists? And then there's a follow-up about whether ESA offers internships.
Well, I guess I'm really encouraging any young person to study science if they have this interest, in particular young women if they have this interest. It's a lot of fun. Of course, it's a lot of hard work, but it's also a lot of fun, and so I think it's really worthy. Yes, as far as I know, ESA does have some internship, and so people can monitor in the ESA website when these internships are happening and how to apply. But as far as I can tell, yes, they do have those internships.
Yes, and to add for young female, sorry, Billy.
No, go ahead.
Sorry. I would say follow your heart. If you're really interested and you're fascinated by science, just do it, because you will need a lot of motivation. It's hard, as Giovanna said. It's not just an easy study, but it is so much fun, and you learn a lot. And you, as a scientist, what personally I like a lot of being a scientist is that we can be excited by something. We can ask questions out of curiosity. How does it work? How are there planets out there? And we can try to convince people, other scientists and people who give funding and agencies who build satellites, and say, look, this is a really great thing we have to find out. And when you're lucky, you get it, and the mission is built and it's done, and it's so much pleasure. And even for smaller projects, you don't have to think only about billion-sized projects, but you can turn your ideas into reality. And this is a lot of fun, and I think it's worth a hard study. And I can only recommend of doing it if you're really interested and fascinated in science.
I just wanted to add about internship at ESA. Yes, they are internship. And I know it for a fact because my daughter did one, and she did one in Washington, D.C. To liaise with NASA and the people in D.C. So yes, and it was very interesting.
Okay, good. Well, the next question, I mean, it's slightly out there, but this is a SETI Institute presentation. So I have to ask about alien megastructures and Dyson spheres. What signature, I'll give this to Giovanna first because she's laughing. What would you see as a definitive detection of, say, a Dyson sphere? Maybe explain what that is to people who are not familiar with the term. What anomalies would excite you in this sense of possibly techno signatures rather than biosignatures?
I was not laughing, I was smiling, because I simply thought that is a very difficult question. And as I said before, I think we still learn the basics of what does it mean to have a habitable planet. And that's why I think ARIEL might contribute more to the question what a non-habitable world might look like before even you get into the habitability. So when it comes to signature of a very intelligent civilization, then of course all the bets are on. And so for the moment, unfortunately, at least for me, is still more in the domain of theoretical speculations. Very interesting, but we're not there yet, at least with missions like ARIEL or similar missions in this decade.
Okay, we can get to the next question then.
Okay, and I think this is the last question, I've been told. So it is, what are the top exoplanets that will be studied in greater detail moving forward? For example, Proxima b, Kepler 452b, etc., and why? And I think maybe Willie might be able to start with that.
Yeah, we have, as I said before, we had this team of 40 scientists headed by Didier Queloz, last year's Nobel Prize winner for having discovered the first exoplanet in 1995, together with Michel Mayor. And they spent, well, we spent together for more than 4 years in trying and arguing exactly what we want to measure. So it depends on the interest of people. Some people, for example, are interested in better characterizing atmospheres of planet, and then following the phase curves gives you some clues about the albedo of the atmosphere, and this can help removing some degeneracies from spectroscopic observations as well. So this is one interest. One set of people in the science team are interested in planet formation and how do planet migrate, form, why are systems the way they are today? Why are there so many planet near or close resonances in systems, and what are these trains of planet? And that you can do, and you can get quite some, for this type of question, the interesting systems are the ones, the multi-planet systems. So planetary system with 3, 4, 5, 6 planets provide quite some strong clues about the formation, because all these objects have been formed in the same system. So you get rid of all the uncertainties about the initial condition of the system. You have to be able to explain the way they look and why they're there from a single set of initial conditions. So they're depending on things. We have people in the group, for example, that try to see if CHEOPS could detect an exomoon. Small planets are difficult. I let you imagine how exomoons are difficult to detect. I'm not sure, but if you don't look for them, you will never find them, right? So this is something, we have a group of people looking at it. We also try to measure all sorts of things. We have asked, because what you need to realize that with CHEOPS has been built as a precision machine. And if we get that precision, maybe 10 times better than what has achieved before, you start seeing new effects. You can see new things. And it is these new things that make the open, in some sense, new windows on these science issues. So this has been the discussion. And so there will be, I hope, a flood of papers soon that show a bit the first result.
And maybe, Giovanna, you want to answer to this question? Since in the landscape of non-planets we have so far, what will be for you the most interesting one to observe with ARIEL?
Of course, for ARIEL, we still have a few more years to go. So clearly the scenario might change. For the moment, we already have a list of planets that we would like to observe. But again, we're expecting this list really to evolve through time. Certainly, I have personally a passion for 55 Cancri E because it's a super Earth orbiting around the star in less than 1 day. So the temperature at the surface is expected to be over 2000 degrees. So the surface is expected to be molten. And we have all sorts of speculation about the atmosphere or non-atmosphere of the planet. And I would really like to know exactly what is happening in that particular planet. But this is my own favorite one. Of course, also in case of ARIEL, there is an entire team that is looking into the target list. But again, we will also make sure that the target list of ARIEL is published well in advance of the launch, and we can receive then, in a certain sense, the vote or the input from the entire community. So clearly, it will not be a choice only of the ARIEL mission.
Okay, thank you. I have a final question for you, something that you have no idea will ask you this question. So I want you to kind of project yourself in the future. for Willy in 5-10 years, for Heike in 10-15, for Giovanna in 15-20 years. And think about your mission and think about what you will think will have been the greatest, the best, the most interesting, the most intriguing discovery of your mission. Like after the mission, imagine, give me something that you think will be the most interesting one and why. We can start with you, Heike, if you're ready.
From my mission?
Yeah, for your mission.
Oh, from my mission. So my mission doesn't go for a particular target. My mission is combining detection with high precision and for statistics. So what we really want is to have a rocky planet of Earth-sized around a solar-like star, and we know it's rocky. We have a density like the Earth. You know, the star is similar, and maybe there's some more planets around it to make it a system. If I dream, you know. But to have these kind of planets and more than one, so we get statistics and we can tell we know how many are out there, how many solar systems are out there. And I mean solar systems, not planetary systems in general. And if we get this from PLATO, for me, this would be the most outstanding results, find an analog to ours, because so far we have not found one and they seem to be rare. And you asked the question about biosignatures and you know the difficulty and about this, you know, it is very difficult to give a clear indication that we find life on another planet if we don't know the life we are looking for. We have to have, I don't know, if you're traveling, I'm sure somebody has said this to you as well, if you're traveling to a new city and you only see what you know. Yeah, if you don't know what is special out there or a bit of the history, you can walk through the city and you don't get the big impression because you don't know what you see. You don't know what to look for. And it's similar. It is similar with finding biosignatures. If you don't know what to look for, it's very difficult to identify it. So to have a system and a constellation of an Earth around the Sun at a similar age, that would be a key target for all future biosignature studies. And if we get that from PLATO, that would be great. And in addition, of course, we have the statistics. How many small planets? What planets with longer periods? You know, the reflected light and the ages, you know, and see planets at different ages. Understand planet evolution really. I'm a planetary scientist. I did comets before I went to before '95 when exoplanets were discovered, and I always thought these astronomers, they know their stars very well, and I was surprised that they don't know the age of a field star to a factor 2. Yeah, so it's very difficult now to sort planets to age and get a sequence and an understanding. And to get this, we need statistics, because the astronomers learned how stars evolved. Because today, if you look outside, you see stars of different ages. But to understand the stellar evolution, you have to you need many to sort them into to understand which ones are really different, and which ones are just different evolutionary state. There was a German astronomer once that I heard 30 years ago in a public talk who said if the aliens would come to Earth and they would see humans, it was Kippenham, a German astronomer, famous astronomer, said if the aliens would come to Earth, they would see humans, and they would see humans which are small. They would see people which are big and yeah, slim and they're all different. And what they would do first, if they are astronomers, they would classify them. They would say there's a type of being that's small and the type of big, and they would need some time to understand that actually it's the small and the big are the same. It's just different evolutionary stages. And this is what the astronomers did for stars. And I think we are really at the edge of being able to do that with planets. And what we need is the precise ages. We need to detect small planets, and many of them. That's what PLATO will give. We need to understand the atmospheres for the hotter, warmer ones, maybe for some great small ones, Giovanna from ARIEL and James Webb. And then we will need the big missions that you are studying in the US to get for the biosignature and the really small planets with small atmospheres. And yeah, if I could, I would wait 50 years and then see what we have. If you put all of these together, it's a big puzzle.
Thank you. Willie, since you're on mute, you're ready to answer to this question? What will be the most significant or fun or intriguing discovery with CHEOPS? Only one, huh?
I have two sides of the coin here. First is because we were a test balloon, my first satisfaction would be that we can show that we managed the test and we passed it and we were able to build something that brings first-rate science in a small ESA mission. Right? This was a challenge. It was to build something fast and cheap that brings top science. So that is, we are on the way to that. I'm sort of getting positive about that part. So that's good. Don't need to wait for 10 years. Because anyway, I will be retired by then. And so it is a whole different ballgame. The other thing is, of course, is because we were all about this precision, measuring a few planets with high precision in order to, constrain further whatever we know about these objects. I think that the victory would be, in, so to speak, in having a set of, I call them Rosetta Stone objects or systems, that for which the precision we managed to obtain allows some change of paradigms on how they formed, how they evolved, how their characteristics are, and so on. And at the same time, the cherry on the cake would be that some of those become favorite targets for JWST or something like this. So, and having helped, this little mission having helped in defining what the golden targets are of these larger infrastructure would be fantastic.
Thank you. And you, Giovanna, you mute, so you can unmute.
So my hope is that ARIEL will be able to give a little bit the big picture of planets in the galaxy. As Heike said, today we have almost a little bit of a tension between astronomers who tends to always want to classify objects, also planets, and so see some trends and perhaps think that planets with similar masses or orbits or type of star will always behave the same, also when it comes to their atmosphere, their chemistry, their weather, and so on and so forth. But at the opposite, we also have many planetary scientists that, on the contrary, like to see planets as unique objects, because they're pointing out the example of the solar system, where all the planets are all very different and they're all quite unique in their history and evolution. And so today we really don't know whether these two extremes, which of the two extremes are correct. Most probably the truth is probably in between. And I would like really to see what is happening and getting to the end of this big question.
Thank you. Thank you very much to the three of you. It was a great conversation. I hope our audience liked this conversation and join us in the future. Thanks, Willie, Heike, and Giovanna. Great having you. Good luck with your missions. And Bill is going to take over and say the last word. Thank you.
Great. Well, thank you, Frank. And let me just echo our appreciation to Giovanna and Heike and Willie for great and inspiring discussions about these missions. And of course, I misled in the beginning talking about forthcoming missions, since of course CHEOPS is already up there doing science. And the first paper, I think Willie mentioned, is maybe due out as soon as next week. So that's very, very exciting. I think what's also exciting and wonderful for us in terms of hosting these events and these lectures is how they demonstrate the ability of science, of space science and exploration in particular, to unite all of humanity, to bring us all together. And it's really a global audience that we've reached today. And I think one thing that we all share in across all of humanity that is perhaps unique to our species is this notion of curiosity. And clearly we have a curious audience with us today. And you could tell by the amazing questions that they asked. And I'm sorry we couldn't get to all of them. We are actually looking at ways to try and address some of these offline after the talks and do follow-up and get them posted. So we'll keep you abreast of that option. And if we're able to address some additional questions and get them posted somewhere, we'll let everybody know. Meanwhile, I thought it'd be fun to share, since we asked you to tell us where you're from, a little demonstration of the global audience we've reached. So we've had people joining us today from Malta, from Chile, from France, including a colleague from the Paris Observatory, from India, from Canada, Switzerland, the UK, Gibraltar, Poland, Germany, Belgium, Scotland, Australia, Venezuela, Guatemala, Brazil, Peru, the Netherlands, and South Africa. So that's a pretty good audience, and it says, you know, how far and wide these topics reach. And here in our own country, the US, we've had friends joining us from California, Hawaii, Texas, Colorado, Illinois, Pennsylvania, New Jersey, Oregon, Alaska, Louisiana, Ohio, Georgia, Arizona, Minnesota, North Carolina, Washington, Florida, Maryland, Tennessee, and New York. So I would have saved time by talking about the states that weren't here. But in any case, it's really wonderful to have all of you here. Thank you for joining us, and we do hope you enjoyed this talk. I do want to also give a special shout out to a very special guest who is also joining us today, and that is Bill Barucki, right here from the San Francisco Bay Area. And of course, our guest speakers know him well, but Bill was the principal investigator for the Kepler mission, that amazing mission that we've talked about so much, that has really changed our perspective of our place in the universe forever, and where the SETI Institute played a huge part in data acquisition and analysis. And I know I've seen some of our colleagues from the Institute as part of the Kepler program joining us today as well. So thanks, and great to have you there with us, Bill, today. Thanks for joining us, as always. Do want to let you know about two upcoming talks that are happening in October in our series. So a very interesting kind of special event, if you will, on October 6th. We're going to be having a conversation with you about the SETI Institute itself. So we do a lot of conversations and talks about different specific topics, but don't do a lot of, make a lot of point to talk about the Institute and the breadth and depth of our science and research and education. So we're going to have the head of research at the Institute here with us, as well as the head of education, also the head of education and outreach and communications, which is actually Simon, who's with us today, joining us. And we'll be talking about all the work we do at the Institute in these areas of research and education and outreach. And of course, our research not only encompasses SETI programs, but of course, astrobiology, planetary science, and so much more. So join us on October 6th. That talk is at 3 p.m. Pacific time. It'll mean staying up late if you're in Europe, but you know, if you've got a sleepless night, it might be a great way to pass the evening. There'll be another talk in October on the 21st. Time is not yet clear, but we're going to be talking about radio telescopes. And we're going to be profiling some of the more famous radio telescopes on Earth and talk about what they do and what they're used for, not only in terms of radio astronomy and cosmology and understanding some of the fundamental aspects of universe and its origins and structure, but they're also the principal tool used by SETI researchers to look for technosignatures or signals from advanced civilizations elsewhere in the universe. So join us for that on the 21st. Go to our website to get the details. And I will also point out, since the question about interns came up, or internships, we do have an internship program here at the Institute as well. And if you'd like to know more about that, visit the education and outreach part of our website at SETI.org and become a member. Sign up to receive our newsletter, our monthly newsletter, and find out how you can get involved and join us and be part of our journey, and maybe even support our efforts to bring this amazing science to you. And last but not least, I'm going to close by saying that our speakers today will be receiving the very special tribute we have for all of our wonderful speakers on the SETI Talk series. So it's this incredible, priceless coffee mug that says SETI Institute, SETI Talks, and it says on the back, I dropped the mic at SETI Talks. And the only people in the world who have these talks are people, or have these mugs, are people who've been our guest speakers. So they're highly valued. I've seen them on eBay at millions of dollars a piece. We'll be sending them by secured transport over to Europe to our guest speakers after this talk. So again, I want to thank you all for joining us today. It was really wonderful. Thanks to our audience for being part of this and for coming along for this journey today. Exoplanets, as far as I'm concerned, are the most exciting and dramatic thing in all of astronomy and astrophysics today. And these missions, both present and forthcoming, are really going to be transformative. So wonderful to learn more about them and have insights into them. And of course, for the missions yet launched, best of luck with those, and make sure they get up and get active. And in the meantime, We hope you'll come back and join us for our next SETI Talks on October 6th and 21. And you'll come and join us and get to know us at SETI.org. We thank you all again. And from Mountain View, California and the SETI Institute and my colleagues, Rebecca and Simon and Lee and Jasmine, who've been supporting us today, thanks to you. And we'll see you all again next time. Take care, everybody.
Thank you, Bill.
Bye.
Thank you.
Thank you.
Goodbye.
Thank you very much.
Bye.
Okay. Thank you.